transfer function of armature control DC motor and transfer function of field control DC motor. We will see now. Transfer function of DC motor. So we are having two types of transfer functions in DC motor. First one is armature control, and second one is field control. So we'll see first armature control DC motor transfer function calculation. Armature control DC motor. So if you see the circuit diagram of the equivalent circuit of the armature control DC motor can be shown like this. So this is the field winding having the resistance RF and the inductance of the field winding LA, and this is the field voltage which is kept at constant, and here this is the armature current IA connected to the DC motor, represented like this, DC motor, and this is plus minus, and this is the armature voltage, and this is the back EMF in the motor, and having the resistance RA and inductance LA in the motor. So these are the motor terminals A and AA and connected to the shaft. So it is a mechanical rotational device having the torque T and the dash moment of inertia J, and the dashpot B having the rotation theta. So this is the equivalent circuit of a DC motor, equivalent circuit of a DC motor. So for this we have to calculate the transfer function by armature control method. So in that armature control method we are keeping field voltage as constant and armature voltage is variable. So in the field control we are keeping armature voltage as constant and we are varying the field voltage. So the circuit diagram is same for both the machines, for both the methods, armature control and as well as field control DC motor. So the basic principle is here. The speed of the DC motor is directly proportional to armature control voltage. So I can write VA and inversely proportional to flux. So speed is directly proportional to VA, or I can write like this, and flux phi. So if I write the armature circuit in the motor, DC motor, the circuit will be like this, having RA and LA, having the back EMF EB, this is the motor back EMF, and this is the armature voltage VA, having the resistance RA and LA, and a current of IA is flowing through the circuit. So if I apply KVL, in the given circuit, so here the equation is VA minus IA into RA minus LA into DIA by dt minus EB is equal to 0. So from this VA can be written as VA is equal to IA into RA plus LA into DIA by dt plus EB. So if I apply Laplace transform here, then this equation will become VA of S is equal to IA of S into RA plus LA into S into IA of S plus EB of S. So I can take IA of S as common here, then the equation becomes now VA of S is equal to, if I take IA of S as common, RA plus S into LA plus EB of S. So this is the main equation, equation number 1. So we need to calculate, we need to find out this IA of S and as well as EB of S, then we have to substitute in the equation number 1. So here another equation in the motor is torque directly proportional to phi into IA. So the torque of a motor is directly proportional to phi into IA. So here it is a armature control, hence the field constant, the flux is kept as constant. So therefore torque is directly proportional to IA. To avoid the proportionality constant, I am replacing with it constant, torque constant KT into IA. So if I apply the Laplace transform for this Laplace transform, then the equation becomes T of S is equal to KT into IA of S. This is equation number 2. Next, back EMF of a motor EB is directly proportional to rate of change of angular displacement theta. So EB can be written as KB into, to avoid the proportionality constant, d theta by dt. So apply Laplace transform to this, applying Laplace transform, therefore EB of S is equal to KB into S into theta of S. This is equation number 3. From the mathematical model, mechanical model, we are having this dashpot, moment of inertia in the motor, so having the torque T and angular velocity theta. So therefore from this torque T can be written as J into d square theta by dt square, this is the dashpot, plus B into d theta by dt. So apply Laplace transform to this, T of S can be written as J into S square theta of S plus B into S into theta of S. Take theta of S as common from this. This can be written as Js square plus B into S. This is what theta of, so torque Ts. This is equation number 4. So from equation 2 and equation 4, we are having the same torque expressions. So from equation 2 and equation 4, KT into IA of S is equal to theta of S into Js square plus Bs. So from this, IA of S can be calculated as theta of S into Js square plus B into S divided by KT. This is equation number 5. So we are having this main equation, equation number 1, VA of S is equal to IA of S into RA plus SLA plus EB of S. So here we are having IA of S value and EB of S value. So simply substitute equation 3 and as well as equation 5 in the equation number 1. That gives the solution. Substitute equation 5 and equation 3 in equation 1. So we will be having VA of S is equal to theta of S, this is IA of S, Js square plus Bs divided by kt into Ra plus S into La plus Kb into S into theta of S. So here S into theta of S can be taken as constant common, then this will be Js plus B into S into La plus Ra divided by Kt plus Kb. Then further it can be written as theta of S Js square plus B S into S into La plus Ra plus Kt Kb into S divided by Kt. So this can be written as, so this is Va of S, which is nothing but theta of S into Js square plus Bs S into La plus Ra plus Kt Kb into S divided by Kt. So here the transfer function of the motor is, output is mechanical rotation theta of S and input is armature control voltage Va of S. So the transfer function can be, transfer function is nothing but Laplace transform of output by Laplace transform of input. So that can be written as Kt divided by Js square plus Bs into S into La plus Ra plus Kt Kb into S. This is the transfer function, and further it can be simplified as Kt divided by, so I am just taking Ra as common from this, so this can be S into La by Ra plus 1, and from this Bs I am taking as common, then J into S square by Bs plus 1 plus Kt into Kb into S. So here this can be written as Kt divided by Ra into B, Ra into B divided by, this will be now S into 1 plus S into armature constant, time constant Ta, 1 plus S into Tm, mechanical time constant Tm plus Kt Kb by Ra into B. So this is the transfer function of DC motor when field control, armature control, by keeping the field control as constant. So similarly for field control, transfer function of the DC motor field control technique. So by keeping armature control as constant, so here Va is kept as constant. In the earlier case we have kept Vf as constant, so here Va is kept constant. Then the field control, the circuit diagram for field voltage, field resistor and inductor can be like this. So there is no back EMF constant in the field. So this is Rf and this is Lf. So applying KVL in this loop, we will get the equation as Vf is equal to If into Rf plus Lf into dIf by dt. So apply Laplace transform on this. Vf of s is equal to If of s into Rf plus Lf into s into If of s. So if I take If of s as common, If of s is taken as common, then it will be Rf plus s into Lf. This is Vf of s, equation number 1. And the torque is directly proportional to field current. Torque is directly proportional to field current. So to avoid the proportionality constant, a time constant, the constant kt into If. So apply Laplace transform for this also. There will be having T of s is equal to kt into If of s. This is equation number 2. And from the mathematical model, so this is the mathematical model. The previous class also we have seen here. This is torque T, this is angular rotation theta, and this is the dashpot B. So from this, torque can be written as J into d square theta by dt square plus B into d theta by dt. So apply Laplace transform to this. Therefore T of s can be written as J into s square into theta of s plus B into s into theta of s. From this, take theta of s as common, J into s square plus B into s. So this is the torque equation T of s, equation number 3. So from 2 and 3, from equation 2 and equation 3, kt into If of s is equal to theta of s into js square plus bs. So from this, calculate If of s, which can be written as theta of s into js square plus bs divided by kt into If of s, kt. So this is equation number 4. So from equation 1 and equation 4, from equation 1 and equation 4, from equation 1 and equation 4, we can write Vf of s is equal to js square plus bs So from this, I can take bs as common, so it will be 1 plus s into j by b, and here I am taking Rf as constant. This will be 1 plus s into Lf by Rf. So this is the transfer function. So I can replace with time constants. V of s can be written as kt by bs, kt by bs into 1 plus time mechanical time constant and s into Rf by, into 1 plus S into electrical time constant Tf. So this is the transfer function of the DC motor with respect to field control.